This video is on magnetic properties of materials. This is going to be somewhat shorter than some of the other ones. It's not going to be as short as the optical properties. As we go through, there's going to be some things that we want to try to keep straight. First, we're going to talk about an electromagnet. An electromagnet is a magnet where the magnetic field is induced by some current, some electron current. And the magnetic field here is called H, and the current of the electrons is I. And so if we do this just for a single wire, there's my wire. And I'm going to have some current here, I. And what we're going to do is we're going to use our right-hand rule. So our thumb points up, we curl around the wire. This is my H field, my magnetic field. And this is what happens when electrons move. When electrons move, we get a magnetic field. So this is interesting, but let us do something a little bit more interesting. We're going to take a coil of wire. So I'm going to take the same wire, and I'm going to loop it around a bunch of times. I'm still going to pass a current. What's going to happen is, again, the magnetic field is going to be induced, but because the wire is now looped up on itself, it sums up throughout all these coils, and we get our magnetic field that comes up this way. And so we get our H field that goes through this coil. So the more coils that I have, the stronger field that I can get. There's a few other things. I'm going to get into the equation probably in a bit. There are some other things that determine the strength of the magnetic field as well. So that's an electromagnet. What's a permanent magnet? A permanent magnet, it's where we don't need to apply the electron movement, the electron flow, but I can still get a magnet. I can still get a magnetic field. Ferromagnetic materials are high susceptibility to magnetization. They're materials that are very easy to magnetize, and they stay magnetized. The strength of a ferromagnet depends on the material that we use. And it may persist, or it will persist if it's ferromagnetic, it may persist after we remove an external magnetic field. So just because I have this material that could be magnetized, it doesn't mean that it is. I can put it in a really strong magnetic field that'll take on that field strength. It'll take some of that, and when I remove that external field, this material will be magnetic. So here's the equation from above for the coil of wires. So we have H, our magnetic field, is equal to the number of turns or the number of loops that we have of our coil times the current that we pass through it divided by the length of the coil, or the height of the coil, however you want to call it. We're going to get another variable here. And this variable is B, and sometimes B and H get kind of mixed together, and it's hard to keep track of which one's which. H is the magnetic field that is kind of around. It's the one that we put things into. What B is it's the magnetic flux density. It's the magnetic induction that a material can take on. And so here's the equation. We have our B, which is equal to mu times H, where mu is the permeability, which is the measure of the ability of a material to support a magnetic field. So how easily can a material support a magnetic field? There is this equation. I'm just going to write off to the side real quick. I can have my magnetic flux density in free space, which is equal to my permeability of free space, times H. What that really means is, what is my magnetic field in a vacuum? That's what free space is. And so if I'm just talking about what is my magnetic field in a vacuum, we can go ahead and we can look at this equation. I want to draw a picture of our materials, though. Again, if I have my coil of wires and I pass a current through here, there's going to be some magnetic field. But if I put, let's say, a piece of iron inside of this coil. I slide a piece of iron inside of this coil. What's going to happen is, because iron is able to do this, it's going to grab on to some of that H field. That H field is going to be larger than the B field that it can take. It can take a portion of that B field, or sorry, a portion of that H field, and it can keep it for itself. So then what happens is I take that piece of iron, and now I can take it away from this coil of wires, and I now have a magnet. Inside of here, we have some magnetic field still. That is our B field. We have some types of permanent magnets. We have a hard magnet. It means that it's hard to magnify a material, but it's hard to remagnify, or I think that should be demagnify. So it's hard to make it hold on to a magnetic field, but it's also hard to demagnetize it once it has that magnetic field on it. An example here would be an electronic generator, an electric generator. There are permanent magnets inside of there, and we want those magnets to stay magnetized. We don't want them just to slowly stop being magnetic or to change. At some point, we want them to hold their field. Another example would just be those simple magnets that we see on cartoons, or maybe they're on your refrigerator, kind of look like a horseshoe. It sticks on your refrigerator because it's a permanent magnet. It's not just going to fall off someday because it decides to stop being magnetized. So that is a hard magnet. A soft magnet means that we can easily magnetize it and we can easily demagnetize it. An example of this is an electronic transformer. So what an electronic transformer is it's a type of metal, normally, kind of shaped like a donut. And what we're going to do is we're going to coil, again, we always come back to these coils with these electromagnets. We're going to coil a wire around one side of this. And I can go ahead and I can pass a current through here. And when I do that, I induce this H field through my coil. But because I have a material in there that can hold on to a magnetic field, this magnetic field is going to pass through the material, through this donut. Okay, that's great. But what do we do with that? What we do is we put a coil of wires on the other side. Well, we have this moving magnetic field, and instead of moving electrons and creating a magnetic field, if I move a magnetic field, I can also move electrons. And so what we have here is if I have some current on this side, I'm able to go ahead and induce a current over here, where in between there's no electrons that are flowing. So I can transfer electric energy this way. Another thing I can do, depending on how many turns the wire and how many turns I have on these coils, I can either reduce or increase the voltage from one side to the other. That's how you can step up or step down voltage. I can also have magnets that are somewhere in between. An example of this would be something like magnetic memory. They don't use that as much anymore, but things like, and they're going away from these, the credit card strips, those black strips on the end, back of your credit card, they're also used for hotel keys. Magnetic tape, and this, I'm not talking about actual tape that's magnetic, it's magnetic strips, such as for cassette tapes or VHS tapes. And hard drives. Old hard drives were, I shouldn't say old, but they're being more and more commonly phased out, but there are hard drives that use magnetic storage. And the way that these work is I have these discs that are made of this material that, again, they're not a hard magnet, but they're not a soft magnet. They're somewhere in between. And we portion this out. These would be our bits of material. And what we could do is I could have some material here. I could have a coil of wire. That's how I control what's happening around that material. And as I pass a current through here, I can change the current going one way or the other way, so I can have the magnetic field either pointing up or I can have the magnetic field pointing down. And as I move this over this material, I can induce magnetization on these blocks. And if I want to read this, I just go over the top of it with something that's a magnet. So I go over it with some type of magnet, and it either gets pulled closer or it gets pulled further away, and then I can tell whether a down arrow was saved there or an up arrow was saved there. And so all these different types of memory are important in our everyday life. Without these hard magnets, we wouldn't have things like electrical generators. Without soft magnets, we wouldn't be able to step up or step down currents, or sorry, voltages. And if we didn't have the things between them, then we wouldn't have things like magnetic memory. So they're all pretty important. So remember that a moving charge induces a magnetic field. So what we're really looking at here is we have an atom inside of a material, and all of its positive charge, and again, the neutrons and stuff are in the middle. But around the outside of it, we have this electron cloud. And in materials that don't bind these outer electrons very strongly, we're able to get those unpaired electrons to kind of point in a specific direction. Now, the electrons themselves aren't pointing, but they are moving, and so they do induce a sense of magnetic properties in a certain direction. So this is why some materials exhibit properties and some don't. So here I phrase it the other way. Why don't some materials exhibit magnetic properties? The short answer is that unpaired electrons, such as iron has 4 unpaired valence electrons, they don't cancel out magnetic fields. If they're a pair, if they're bonded together, if it's a strong bond, those two electrons tend to work against each other, but iron has unpaired electrons, and so we can get a magnetic field out of those. Now, there is a long answer, and the long answer is actually very short at first. The long answer is, well, all materials exhibit magnetic properties. We just can't see them. And so now we're going to talk about the magnetic properties of all materials, not just about those really, really strong ferromagnetic permanent magnetic materials. So I have a picture here of this arrow, and this arrow here is my H field. And so if I have this H field and I get a material that is ferromagnetic, what it's going to do is it's going to induce a magnetic field in my material. My material is going to take some of that magnetic field. That magnetic field is going to go in the same direction as this induced H field. The material can stay magnetized once this H field is gone. So I can actually remove my material from this H field, and now it has its own field as well. And the reason this happens is because its magnetic domains align. And I'll talk about what magnetic domains are really quickly. But first I'm going to say, all right, so I have this large H field, and what's going to happen with a ferromagnetic material? It's going to take some of that magnetic field strength into itself, and that would be our B field for our ferromagnetic material. All right, before we get to paramagnetic and diamagnetic, I want to jump down and talk about what these magnetic domains are. Magnetic domains, these are like, but are not, grains, our grain structure. All of our atoms have these little magnetic moments in them. And when I have a whole bunch of them together, they are able to align, making up domains, large chunks of our material that tend to want to be magnetized in the same direction. If the domains align, then the material will exhibit magnetism. So I can look at this maybe with 3 pictures. The first picture here is on a really, really small scale, atomic scale. I have a material and its atoms are free to have a magnetic field in really any direction. If I look at this a little bit larger, materials that are nearby, just because it's easier on an energy standpoint, it's low energy to do this. Remember, everything comes back to energy. I've zoomed out, and I'm looking at something that, again, looks like grains, but these aren't grains. These are magnetic domains. But groups of atoms will tend to want to align together, again, because it's energetically favorable. But what I can do is I can put this material in a H field. And if I put it in this H field with this H arrow going to the right, like we had up above, what's going to happen is these domains are going to start to align. Now that all these domains are aligning, my material will start exhibiting properties of magnetism in that direction. So that's what a magnetic domain is. It's where we have groups of atoms that we call domains. Those will line up together because of energetically favorableness. And if I can get domains to line up, then my entire material will act, well, just like this picture up here. We'll get a B field in that same direction as H for our ferromagnet. And I can even remove that H field from it, and I get a permanent magnet. Paramagnetic material. The field will be the same direction as the induced field. However, the material won't stay magnetized once the field is gone. So this is kind of the picture of if I get like a nail and I put a magnet on the end of the nail, I can use that nail to pick up other nails, because what's happening is some of that field from my magnet is getting transferred into the nail. But as soon as I remove that magnet from my nail again does not act like a magnet anymore. The reason for this is because there's a balance here. Again, it's an energy problem. I'm going to go ahead and draw my B field up really quick for a paramagnetic material. It's going to be weaker than for a ferromagnetic normally. There's two things here. One is the magnetic energies would like to align because it's energetically favorable, but at the same time, there's thermal energy inside my material. And so my material, the atoms have some thermal energy and it's free to move around. What we have here is a balancing act. For a ferromagnetic material, the magnetic domains can align and the thermal energy isn't enough to disrupt that alignment. But for a paramagnetic material, once that H field is gone, it's no longer energetically favorable for those domains to stay aligned. The thermal energy is too strong and the domains will slowly change and they will no longer be aligned. So it'll go back to this middle picture here once the H field is gone. The last one here, and this is what most materials actually fall into, is diamagnetic. Diamagnetic, the field, the B field, is actually in the opposite direction of our induced H field. Every material is diamagnetic, and they have very, very small magnitudes. So when I say all materials, I really mean it. There are some interesting videos online about diamagnetic materials, and you can even find videos where they levitate living creatures. There's one where they levitate a frog. It's a very, very strong field, and the frog is very, very small. Everything exhibits a diamagnetism, but you need an extraordinary strength H field to be able to see those. So I do have a little bit more information on those. All materials are diamagnetic. If there is some net magnetic moment, then they are paramagnetic. So the first one, all materials are diamagnetic. If there is some net magnetic moment, so I have this middle picture here, then materials paramagnetic. I can align those if I need to. If there is long-range ordering of magnetic moments, this picture on the right, then they are ferromagnetic materials. Ferromagnetic and paramagnetic properties will overpower the influence of diamagnetism. So even a permanent magnet is diamagnetic. It has some field that opposes this ferromagnetic B field, but it's so small that these ferromagnetic and these paramagnetic B fields override any diamagnetism that we see. All right, so I have a graph that I'd like to draw. We have our B field on our y-axis, our H field, or sorry, our B field on our y, H on our x, and we're going to put somewhere along here our mu naught, our permeability of free space. And again, that mu is used to figure out kind of our flux density, what our material can take into itself to become magnetized. That's what our mu is for. If I have a large positive mu, larger than, I guess I should say mu naught, it's above mu naught, then this is my mu for a ferromagnetic material. If I have one that is large, let me get a different color here. It's larger than, but it's not significantly larger than my mu naught. This is my mu for my paramagnetic material. And I have a mu for diamagnetic. It would actually be underneath my mu naught. So that's just kind of picturing what's going on here with our mu's, our permeability, so that we could calculate something like our H's and our B's. We're going to go over a magnetic hysteresis loop or a magnetic hysteresis curve. A hysteresis is a phenomenon where the property that we see kind of lags behind the cause of what happens. This might be a bad example, but to just kind of picture it, I think about cartoons where the cause of a character falling off a cliff sometimes happens long before the character actually falls. There's that lag. There's some time difference before they fall. In real life, you walk off a cliff, that would be bad. There's an air mattress or something at the very bottom, so you're not going to get hurt. But you go off the cliff, you're going to fall immediately. Gravity pulls you down immediately. But on the cartoons, you stand there and they kind of wait and they look around and then they start falling. That's the idea of hysteresis. The phenomenon lags a little bit. All right, so what we have here is if I have a material, remember that's what my B is, that's going to be my material property. If I have a material and I put it in an H field and I start increasing my H field, nothing happens for a little bit. But what's going to start happening is it's going to start taking some of that H field and turning it into its own B field. But at a certain point, it maxes out. It can't take any more B field. It maxes out. It doesn't matter how much more H field, how much stronger the H field is. I could go on, forever, but it's not going to be able to accept more magnetic flux. It's not going to be able to increase its B field. So what we do is we say, all right, so we're not gaining any more B, so we start reducing our H field, and we reduce it down to 0. Well, if it's a ferromagnetic material, it holds on to that B. So our H is back at 0, that H field is gone, but our material has a B field associated with it. What I could do is I could then put a negative H field on there. I could start saying, all right, well, let's put a negative H field on here. And what do we see? We see that it still maintains its positive B field up to a point. I put this H field on there, and at a certain point, it's going to flip, and it's going to say, I can't resist this H field anymore, and so it flips to this negative B field. And again, it's going to max out somewhere on this negative B field. I can keep increasing my H in a negative direction, and it's not going to add any more negative B, or opposite B, I should say. And so what I do is I remove my H field, and it no longer has any H field around it. But now it has an opposite magnetic field, opposite direction. So what happens is I add a positive H field again, and it flips. And so I get this loop, this curve, that kind of has this square-looking shape that has these little fins on the side. And this is a hysteresis loop. And we can do hysteresis loops for all different types of magnetic materials. I'm going to do them for 2 of them, and it would be good for you guys to think about how some other ones might look. So the ones I'm going to do is I'm going to do one for a hard material, not a hard material, a hard magnet. I have my B field, I have my H field. It's going to look very similar to what we just did. I'm going to use a different color though. I don't like that already. All right, so it's very hard to magnetize, but eventually it does. Very hard to demagnetize, but eventually it does. And so we get this picture that looks something like this. Hard magnets, their hysteresis curve is very, very broad because it's very, very hard to magnetize and demagnetize to change its magnetization. I got to get really far out here on my H axis to make those changes. I know I kind of went over into my soft magnets graph over here, but that's okay because a soft magnet is opposite. It's very, very easy to induce a field and to change a field. So a soft magnet is going to be pretty narrow. It's not going to be able to, it's going to be much, much smaller. The last thing I want to discuss is the Curie temperature. The Curie temperature is the temperature which a permanent magnet will lose its properties, or its magnetic properties will change. All right, on the y-axis here, we have our saturation of magnetization. Sat of mag. Saturation of our magnetization. And on our x-axis, we have our temperature. Now, depending on the material that we have, of course, this is going to look a little bit different on the material. I'm going to have a material saturation at a certain temperature, and I'm going to have what we call the Curie temperature. And we're going to end up getting some type of curve that looks like this. And we really just have 2 regions that we are concerned with. We have our ferromagnetic region, and we have our paramagnetic region. If I'm below the Curie temperature, then my material is going to be able to hold its magnetization, its permanent magnetism. If I heat up a material, it's going to lose its permanent magnetism. It'll end up acting like a paramagnet. And again, if we go back up here to what a magnetic domain is, the only reason that our material wants to align in some cases and unalign in others comes down to thermal energy. Well, that's what we have here. If I take a ferromagnet and I add thermal energy myself, not just room temperature, but I throw it in an oven, I put a flame on it or something, I can add enough thermal energy to where a ferromagnet will act like a paramagnet. Magnets are pretty interesting. There's a lot to them. This was just a really quick basis, a really quick overview about magnetic materials.